This is the lecture for Section 2.2, Modular Arithmetic. In the previous section, we defined z sub n as the set of congruence classes modulo n. The importance of z sub n arises from the fact that we can impose an algebraic structure on it. To do so, we want to define an addition and multiplication on the elements of z sub n. Now note that the elements of z sub n are sets rather than numbers. So we need to define what we mean by the sum or product of two sets. Suppose the class of A and the class of C are two elements in z sub n. We tentatively define the sum of the classes A and C to be the class containing A plus C. Or in symbols, the class of A plus the class of C is equal to the class of A plus C. We use circle plus to denote the addition of congruence classes to distinguish it from ordinary addition of integers. We have a similar tentative definition for multiplication. The product of the classes A and C is the class containing the product AC. Or in symbols, the class of A and then circle dot for the product class of C is equal to the class of AC. For example, let's consider Z5, which contains the classes 0, 1, 2, 3, and 4, where the classes are as shown. Now note that the class of 2 is equal to the class of 17, and the class of 4 is equal to the class of -1. We want to compute the class of 2 plus the class of 4, and the class of 17 plus the class of -1. We can also compute the class of 2 times the class of 4 and the class of 17 times the class of -1. So the class of 2 plus the class of 4, according to our definition, will be the class of 2 plus 4, which is equal to the class of 6, and the class of 6 is equal to the same as the class of 1. Class of 17 plus the class of -1 will be equal to the class containing 17 plus -1, which is equal to the class of 16, which is also equal to the class of 1. And so therefore the class of 2 plus the class of 4 is equal to the class of 17 plus the class of -1. So this seems to show that it doesn't matter whether we use 2 or 17 for the first class, or 4 or -1 for the second class, we obtain the same result for our sum. Well, for the product, we have the class of 2 times the class of 4, which is equal to the class of 2 times 4, which is equal to the class of 8, which is equal to the class of 3. Then the class of 17 times the class of -1 will be equal to the class of 17 times -1, which is the class of -17, which will be equal to the class of 3 as well. And so then the class of 2 times the class of 4 is equal to the class of 17 times the class of -1. So it seems to show that it doesn't matter whether we use 2 to represent our first class or 17 and 4 to represent our second class or -1, we obtain the same result for the product. Now we have to be careful with our definitions of addition and multiplication in z sub n because each element of z sub n can be written in different ways. In the preceding example, we seem to get the same result for the sum or product if we use different class representatives. But we need to show that this will always be the case, that the sum or product of two congruence classes will be the same no matter how we've written them. The following theorem shows that this is indeed the case. This tells us that the addition and multiplication on z sub n are well defined. So this is Theorem 2.6, and what it says is for all classes A, B, C, and D in z sub n, if the class of A is equal to the class of B, and the class of C is equal to the class of D, then the class of A plus C is equal to the class of B plus D, and the class of A times C is equal to the class of B times D. So for our proof, we'll suppose the class of A, class of B, class of C, and class of D are arbitrary congruence classes in Z sub n. We'll suppose the hypothesis, the class of A is equal to the class of B, and the class of C is equal to the class of D. And we need to show the class of A plus C is equal to the class of B plus D, and the class of A times C is equal to the class of B times D. Now by Theorem 2.3, since the class of A is equal to the class of B, then A is congruent to B mod n. And since the class of C is equal to the class of D, then C is congruent to D mod n. Theorem 2.2 implies then that we can add our congruences and we obtain A plus C is equal to B plus D mod n. And we can also multiply the congruences to obtain A times C is congruent to B times D mod n. Then by Theorem 2.3 again, these congruences imply that the class of A plus C is equal to the class of B plus D, and the class of A times C is equal to the class of B times D. So this proves what we needed for the theorem. Now that we know our tentative definitions of addition and multiplication on Z sub n are well defined, we can formally state them. So addition and multiplication in Z sub n is defined as follows. For all class of A, class of C in Z sub n, the class of A plus the class of C is equal to the class of A plus C, and the class of A times the class of C is equal to the class of A times C. Now, just as we do for integers, we can use exponents to represent repeated multiplication in Z sub n. So the class of A raised to the nth power will be the class of A multiplied times itself n times. For an example, now that we've defined addition and multiplication on Z sub n, we can construct addition and multiplication tables. So here are the tables for Z sub 5. First we have our addition table. So we have the entries 0, class of 1, class of 2, class of 3, class of 4 listed along the top and on the left. And then we can fill in the entries. So the class of 0 plus the class of 0 is just the class of 0. The class of 0 plus the class of 1 is the class of 1. And we can continue. So note that the class of 2 plus the class of 3 will be the same as the class of 5, which is equal to the class of 0. The class of 2 plus the class of 4 will be the class of 6, which is the same as the class of 1. And then continuing. And so there's our addition table for Z sub 5. And then we can also construct our multiplication table. And the first row, we're multiplying the class of 0 times each of the elements, and so these will all be 0. And then in the second row, we're multiplying the class of 1 times each of our elements, and these will just be the original elements. And then we have the class of 2 times the class of 0 will be the class of 0. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, which is equal to 1, and 2 times 4 is 8, which is equal to 3. And then we have 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6, which is 1, 3 times 3 is 9, which is 4, 3 times 4 is 12, which is the same as the class of 2. And then we have our final row, 4 times 0 is 0, 4 times 1 is 4, 4 times 2 is 8, which is equal to 3, and 4 times 3 is 12, which is equal to 2, 4 times 4 is 16, which is equal to 1. And there's our multiplication table for Z5. And then we can also look at the addition and multiplication tables for Z6. So we have our elements, the class of 0, class of 1, class of 2, class of 3, class of 4, and class of 5. And then just filling in the entries. These are relatively straightforward. And then our multiplication table for Z6. So our first row will all be zeros. Second row will be the original elements. And then we have 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, which is 0, 2 times 4 is 8, which is 2, and 2 times 5 is 10, which will be the same as the class of 4. And then 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6, which is the same as 0, 3 times 3 is 9, which is the same as 3, 3 times 4 is 12, which is the same as 0. 3 times 5 is 15, which will be the same as 3. And then 4 times 0 is 0, 4 times 1 is 4, 4 times 2 is 8, which is the same as 2, 4 times 3 is 12, which is the same as 0, 4 times 4 is 16, which is equal to 4, and 4 times 5 is 20, which will be the same as 2. And then 5 times 0 is 0, 5 times 1 is 5, 5 times 2 is 10, which is equal to 4, 5 times 3 is 15, which is the same as 3, 5 times 4 is 20, which will be the same as 2, and 5 times 5 is 25, which will be the same as 1. And so there's our multiplication table for Z6. Now that we've defined an addition and multiplication on Z sub n, we want to compare the properties of these operations with the properties of addition and multiplication on Z, which are listed here. So we have first closure under addition for all integers a and b, a plus b is in Z. The associative law of addition for all a, b, c in Z, a plus the quantity b plus c is equal to the quantity a plus b plus c. The commutative law of addition for all a, b, and z, a plus b is equal to b plus a. 4 is the existence of an additive identity, and this says there exists an element, namely 0 in z, such that for all elements a in z, a plus 0 is a, and 0 plus a is a. And then 5 is the existence of additive inverses. So for each element a in z, there exists an element x in z such that a plus x is equal to 0. 6 is closure under multiplication for all a, b, and z, a times b is in z. 7 is the associative law of multiplication for all a, b, c in z, a times the quantity b times c is equal to the quantity ab times c. 8 is the commutative law of multiplication for all a, b, and z, a times b is equal to b times a. 9 is the two distributive laws for all a, b, c in z, a times the quantity b plus c is equal to ab plus ac, and the quantity a plus b times c is equal to ac plus bc. 10 is the existence of a multiplicative identity. So there exists an element, namely 1 in z, such that for all a in z, a times 1 is a, and 1 times a is a. And 11 is the zero factor property for all a, b, and z. If a times b is 0, then a is equal to 0 or b is equal to 0. So these are all the standard properties of addition and multiplication in the integers. And what we're interested in looking at is which properties hold for Z5 and for Z6 and for Z sub n in general. So now by examining the operation tables, we can verify that the first 10 properties hold in both Z5 and Z6. For instance, to verify 1 in Z5, note that the sum of any two elements in Z5 is also in Z5. So for any two elements in Z5, their sum in the addition table belongs to Z5. Now the element, the class of 0, is an additive identity, since for all classes a in Z5, a plus 0 will be equal to a, and 0 plus a will be equal to a. Therefore, property 4 holds. Now there exists an additive inverse for each element in Z5, since 0 plus 0 is equal to 0, 1 plus 4 is equal to 0, 2 plus 3 is equal to 0, 3 plus 2 is equal to 0, and 4 plus 1 is equal to 0. So the additive inverse for 0 is 0, the additive inverse for 1 is 4, the additive inverse for 2 is 3, the additive inverse for 3 is 2, and the additive inverse for 4 is 1. So therefore property 5 holds. Now by examining its multiplication table, we see that property 11, the zero factor property, holds in Z5. For all elements A and B in Z5, if their product A times B is equal to 0, then either A is 0 or B is 0. This is shown by looking at the multiplication table for Z5. The only entries that in the table that equal 0 are along the first row or the first column. However, this property does not hold in Z6. So for instance, in Z6, 2 times 3 is equal to 0, but 2 is not equal to 0 and 3 is not equal to 0. We want to now prove that the first 10 properties hold in general in Z sub n. And this is theorem 2.7. So let n be a positive integer. Then Z sub n satisfies the following properties. And so we have first 1, closure under addition. For all classes A and B in Z sub n, A plus B is in Z sub n. 2, the associative law of addition. For all classes A, B, C in Z sub n, the class of A plus the sum of the quantity B plus C is equal to the quantity A plus B plus C. The commutative law of addition for all classes A, B in Z sub n, A plus B is equal to B plus A. The existence of an additive identity. So there exists an element, namely the class of 0 in Z sub n, such that for each class A in Z sub n, A plus 0 is A and 0 plus A is A. And then 5, the existence of additive inverses. For each class A in Z sub n, there exists an element X in Z sub n such that the class of A plus X is equal to the class of 0. 6, closure under multiplication. For all classes A, B in Z sub n, A times B is in Z sub n. 7, the associative law of multiplication. For all classes A, B, C in Z sub n, A times the quantity B times C is equal to the quantity A times B times C. The commutative law of multiplication. For all classes A and B in Z sub n, A times B is equal to B times A. The 2 distributive laws. So for all classes A, B, C in Z sub n, we have A times the quantity B plus C is equal to A times B quantity plus quantity A times C, and then quantity A plus B times C is equal to the quantity A times C plus the quantity B times C. And finally 10, the existence of a multiplicative identity. There exists an element 1 in Z sub n such that for all A in Z sub n, A times 1 is A and 1 times A is A. Okay, so we're not including the zero factor property in the theorem since we've seen that that does not necessarily hold in Z sub n. Okay, to prove the theorem now, well, first off, properties 1 and 6 follow immediately from the definition of addition and multiplication in Z sub n. So those are the 2 closure properties. To prove 2, we need to show for all classes A, B, C in Z sub n, A plus the quantity B plus C is equal to the quantity A plus B plus C. So let's suppose that A, B, and C in Z sub n are arbitrary congruence classes. The left side of the equality is A plus the quantity B plus C, and according to the definition of the addition of congruence classes, this will be the class of A plus the class of B plus C, which is then equal to the class of A plus the quantity B plus C. And the right side is the quantity class of A plus the class of B plus the class of C, and this will be equal to the class of A plus B plus the class of C, which is equal to the class containing, or the class of, the quantity A plus B plus C. Now, by the associative law of addition in Z, A plus the quantity B plus C will be equal to the quantity A plus B plus C. And so therefore, the 2 classes are the same, and so therefore the left side is equal to the right side as required. And so this proves property 2. The proofs of properties 3, 7, 8, and 9 will be similar to that for 2. Okay, each of these hold because the corresponding property holds in Z. Now to prove property 4, we need to show for all classes A in Z sub n, class of A plus the class of 0 is equal to A is equal to the class of 0 plus the class of A. So if we suppose that A in Z sub n is an arbitrary congruence class, then the class of A plus the class of 0 will be equal to the class of A plus 0, which is equal to the class of A, and the class of 0 plus the class of A will be equal to the class of 0 plus A, which is equal to the class of A. So 4 holds. The proof of property 10, the existence of a multiplicative identity, will be similar to the proof of 4. To prove property 5, we need to show for all classes A in Z sub n, there exists an x in Z sub n such that the class of A plus x is equal to the class of 0. So let's suppose that A in Z sub n is an arbitrary congruence class. We need to show there exists an x in Z sub n such that A plus x is equal to 0. So we're going to choose x to be the class of minus A. Since A is an integer, then minus A is also an integer, so x equal the class of minus A will belong to Z sub n. And this satisfies the equation since the class of A plus the class of minus A will be equal to the class of A plus minus A, which is equal to the class of 0 as required. And so therefore property 5 holds. And this completes the proof of the theorem. Now, since Z sub n has only a finite number of elements, we can solve equations in Z sub n using exhaustion by substituting each element and testing whether it satisfies the equation. For an example, let's solve the equation x squared plus the class of 5 times x is equal to the class of 0 in Z sub 6. So Z sub 6 consists of the elements 0, 1, 2, 3, 4, and 5. So we just need to substitute each of these into our equation. And so we obtain for 0, 0 squared plus 5 times 0. This will be equal to 0 plus 0, which is equal to 0. So 0 is a solution. For 1, we'll have 1 squared plus 5 times 1, which will be equal to 1 plus 5, which will be equal to 6, which is 0. So 1 is a solution. For 2, we obtain 2 squared plus 5 times 2, and this is equal to 4 plus 10, which is equal to 4. So 4 plus 4 is equal to 8, which is equal to 2. So 2 is not a solution. And then 3 squared plus 5 times 3, this will be 9, which is equal to 3. And then 5 times 3 is 15, which is also equal to 3. So this is 3 plus 3, which is 6, which is 0. And then finally 4 squared plus 5 times 4, this will be 16, which is equal to 4. And then plus 20, which is equal to 2. So we have 4 plus 2, which is 6, which is equal to 0. So 4 is also a solution. So we can see that this equation has solutions 0, 1, 3, and 4. Whoops, I'm sorry, I left off 5. So 5 gives us 5 squared plus 5 times 5, which is going to be 1 plus 1, which is 2, which is not a solution. So therefore the equation has solutions 0, 1, 3, and 4. So you can see things behave a little bit differently in Z sub 6 at least, because we have a quadratic equation with 4 solutions. And so that's a little bit different than what occurs in the integers or rational numbers or real numbers, where a quadratic equation can have at most 2 solutions. Okay, so this finishes up section 2.2.